Hi all, let's take a look at your practice for your fourth test of the semester. Remember, this one will be covering sections 4.3 through 4.8. It's our shortest test of the semester by a considerable margin. So just please make sure that you do understand each of the problems on the test though, because since there's a reduced number, only 12, they'll be worth more each question. The first question would come from section 4.3, the very first thing in this portion of material where we talked about the mean value theorem. I'm asking you to verify the mean value theorem for the function square root of x from 1 to 9. So remember, on the interval a, b, a is just your beginning point, b is your ending point. So the logic of the mean value theorem just simply states that we know that the instantaneous rate of change is equal to the average rate of change on any interval. So if you're on a 2-hour trip and you travel 100 miles, then you've averaged 50 miles per hour. Well, the mean value theorem would say that you had to at least be going exactly 50 miles per hour at least once during the time of that trip. Well, in this problem, the way that is going to play out is you say, well, we need to find the average rate of change of this function from 1 to 9. So we say, well, okay, all I have to do to find the average rate of change is I can go ahead and I can say, well, that's going to be f of b minus f of a. Find the y value at the end point minus the y value at the beginning point. In this problem, you just plug each of these into your function, you get the square root of 9 minus the square root of 1 over the change in x, 9 minus 1. So you can say, all right, then the average rate of change, we can see that the y values went up 2 units in the spans of time that the x values increased 8 units. So you can say, well, then the average rate of change is 2 over 8. That would reduce down to 1 over 4. So on average, the y value goes up 1 unit per 4 x unit increase in this region. Well, what the mean value theorem guarantees is that we know the derivative, which has to give you the instantaneous rate of change, has to equal 1 over 4 for some value of x between 1 and 9. I just have to show that. So now I say, okay, take that derivative. Derivative of x to the 1/2 is 1/2 x to the negative 1/2. And then I can say, well, that's the same thing as 1 over 2 on the root of x. I set that equal to the average rate of change 1 over 4. And in this case, you can just say, well, okay, you could cross multiply, or you could just say, hey, your denominators have to be the same. That's going to give you 2 on the root of x is 4. Divide by 2, that gives you the root of x equals 2. Square both sides, you get x equals 4. Well, we're done because we know that the derivative is equal to the average rate of change at x equals 4, and x equals 4 does belong to the set of values between 1 and 9. Thus, the mean value theorem is verified. Now, for the second and third problem, these also the second problem comes out of 4.3. The third problem actually comes out of 4.4. This is where I'm using the first and second derivative test. When you're using the first and second derivative test, I do want to see your first derivative sign test chart, and for the second derivative, your second derivative sign test chart. So I'll put a problem in which I'm asking you to use the first and second derivative test on the exact same function, just like I did on this practice test. On this practice test, your function was f of x is equal to 3x to the 5th minus 5x to the 4th plus 1. Well, first derivative of that's the 5 comes down, we get 15x to the 4th minus 4 times 5, 20x cubed. We set that first derivative equal to 0 because we know that's where the critical points exist. Now, it's much easier to set something equal to 0 if you can factor it. So always try to factor what you have left over here. Between 15 and 20, I can factor out a 5. Between x to the 4th and x to the 3rd, I can factor out the x to the 3rd. So I factor out that common factor of 5x to the 3rd. When I do, I'll have left over 3x to the first in the first term, and then the x cubes cancel in the second term. 20 divided by 5 leaves me a 4. My factors are 5x cubed times 3x minus 4. We set those equal to 0. The zero product property says, well, those are equal to 0 if either the first factor is equal to 0, and the only way 5x cubed can equal 0 is if x is 0, or if the second factor equals 0. 3x minus 4 is 0 when 3x is equal to 4. Solve for x, and you'll get x equals 4/3. Okay, so now I have my two critical points, but I don't know if those critical points are maxima or maximum points of maximum, points of minimum. I don't know. So we need to find that out. We find that out by setting up a first derivative test. You break up the domain of the original function, which is automatically all real numbers since it's a polynomial. And you'll say, well, I'm going to start at negative infinity, go to your lower critical point, 0. My first test interval is negative infinity to 0. Then go from your lower critical point to your upper one, 0 to 4/3. Then go from that upper critical point of 4/3 up to infinity. In each of these test intervals, you'll choose test points. So I needed to choose a test point between negative infinity and 0. I chose -1. Any number in that interval would have been fine. A number between 0 and 4/3, I chose 1. And a number between 4/3 and infinity, I chose a 2. Now, with each of these test points, what you'll do is you'll plug them into your first derivative. I strongly prefer to use the factored version of the first derivative because all we ever need to know is the sign of the first derivative. We know when the first derivative is positive, it tells us that the slopes are going up. When the first derivative is negative, the slopes are going down. So we can say, well, clearly, when the first derivative is positive, the original function increases. When the first derivative is negative, the original function decreases. So, okay, if I plug a -1 into the factor 5x cubed, I get a negative. If I plug a -1 into 3x minus 4, it'd be -3 minus 4 would be a -7. So both factors are negative. Well, I know the product of two negatives is a positive. Could you actually put the specific number and say, well, John, it's going to be a -5 times a -7, thus it's a +35. You could, but again, the only thing you care about is that it is positive there. The 35 is just additional information you don't need. When I plug a 1 in, the first factor is going to be positive. The second factor would be 3x minus 4 is going to be a negative. The product of a positive and a negative is a negative. So I can say, all right, my first derivative is going to be negative for every x value between 0 and 4/3. To test the next region, I plug in a 2. 5x cubed is going to be positive. It would be positive 5 times 8 is 40. When I plug a 2 into the second group, I would get 6 minus 4. That's a +2. The product of two positive numbers is going to be a positive. And again, you could get a specific number there, but the only thing you care about is the sign of it. So now, the answer that I want to see based on this first derivative sign test is that you can understand, okay, the original function f of x is going to be increasing whenever the first derivative is positive. So it's increasing from -infinity to 0 union 4 to infinity. That would be my answer for that part. It's going to decrease whenever the first derivative is negative. We can see, well, then it's going to decrease between 0 and 4/3 here. Then I would want you to list any maximum or minimum values. The only points that are possible maximum or minimum values are these x values that our critical points are at. So you say, okay, any maximum or minimum is going to occur at a critical point. So I test each of my critical points. Well, what do I know happens before 0? The function is increasing before 0. It decreases after 0. Since the derivative is positive before and negative after 0, I know 0 is the location of a maximum. And again, you can think of it, it's increasing before 0, decreasing after 0. 0 has to be the location of a maximum. Now, if you think about 4/3, It's going to be decreasing before 4/3, increasing after, according to what we have here. So I know x equals 4/3 is going to be a minimum since it's decreasing before, increasing after. So that's why I have minimum for 4/3. This is our first derivative sign test. Now for the second derivative sign test, I still have the same original function. So you'll see I still have f of x is that 3x to the 5th minus 5x to the 4th plus 1. We already found this in our first derivative test. So now I just need to do the second derivative test. I take the derivative again. When I do, I'll get 60x to the 3rd minus 60x squared. And then at that point, just like I do with the first derivative sign test, you want to factor that second derivative so you can set it equal to 0. This one's easily factored. You can just say, well, they have a common factor of 60 and x squared. When I factor that out, I'll be left with x minus 1. Now, I know that 60x squared times x minus 1 can equal 0. When it does equal to 0, that's going to be your possible inflection point. You'll see I named that a pip. Not every time your second derivative is equal to 0. It's not always an inflection point. It's only an inflection point if the second or if the original function changes concavity. The second derivative will have to change sign at each of these points in order for it to be an inflection point. So we're supposed to determine concavity and inflection. So I can say the only possible points where this graph could change concavity are at these two values. So now with that in mind, I need to go in and do my second derivative test. Same as with my first derivative test, I need to break up the domain of the function with these possible inflection points. So I go negative infinity to 0, and then from 0 to 1, and then from 1 to infinity. Now, in checking that first interval between negative infinity and 0, I chose a negative 1. Between 0 and 1, I let my test point be 1/2. Between 1 and infinity, I chose a 2. Now, what do we do with each of these test points? We plug them into the second derivative. This is called the second derivative test. It's better if you choose the factored version of your second derivative. It's easier to plug in. And I can say, well, okay, this first factor of 60x squared. Well, anytime you have an x squared term, it's not going to matter whether you plug a negative or a positive into it. It's always a positive. So I can just say that 60x squared is not going to contribute to any sign changes of the second derivative. It's always positive. It's that second linear factor that's going to create the sign changes. When I plug a negative 1 into x minus 1, I get negative 1 minus 1. That's a negative. When I plug a 1/2 into x minus 1, it's still going to give me a negative 1/2. 1/2 minus 1 is a negative 1/2. So I get a negative for the first factor for both of my, for the second factor for both of my first two regions. In my last region where I test point is 2, if I plug a 2 in, 2 minus 1, that second factor would be positive. Now I can see that in the first and second regions, I have a negative times a positive. Anytime you have a negative times a positive, you know the product is a negative. This tells me that my original function is concave down from negative infinity to 0 and from 0 to 1. You have to put this region to 0 and then from 0 to 1, from negative infinity to 0 union 0 to 1, because the graph is not concave down at 0. I could see someone thinking, well, why can't I just say it's concave down from negative infinity to 1? Because for an instant, it's no longer concave down. Now, 0 is not a point of inflection because the graph didn't change inflection there. It was concave down before and it was concave down after. But it is a point of what we would call concave neutrality. It's neither concave up nor concave down at that point. So it's concave neutral at x equals 0. So that's why it's not included into either of our concave down regions. Now, for the concave up portion, well, when the second derivative test had both factors as a positive, multiply to give me a positive, that's evidence that my original function has to be concave up in that region from 1 to infinity. And you can see that I've put that over here. So now as far as the inflection points, the only possible inflection points were when our second derivative is equal to 0. But at an inflection point, the graph has to change concavity. Well, it did not change concavity from the first region to the second region. You say it's concave down before, concave down after. Thus, 1 is not an inflection point. It's just a point where the inflection is neutral. And then at x equals 1, it's concave down before, concave up after. You can see, well, it did change inflection at 1. Unlike 0, where it didn't change inflection, it did change inflection at 1. Thus, we have an inflection point at 1. Now, the 4 L'Hopital problems, please do keep in mind, I will make certain that of the 4 L'Hopital problems, one of the problems you should not use L'Hopital on. So I'll say use L'Hopital when needed. It'll be needed on 3 of the 4 problems. There's one of the problems where you should not use L'Hopital. Now, on this, we say, okay, when I tried to look at the first limit problem, if I just tried to plug in a 2, your numerator here, you'd say, well, that's 2 cubed minus 8, that's 8 minus 8, you'd get a 0. If you tried to plug a 2 into your denominator, you would get 16 plus 4 minus 20, that's a 0. 0 over 0 inside of a fractions form, that's one of our indeterminate forms that L'Hopital can help with. So I automatically must show that. I can say from this step to this step, I can't evaluate here. It's indeterminate as x approaches 2. So I use L'Hopital and must show the h over the equal sign and say this is the limit as x approaches 2 of the derivative of the numerator, which is just going to give me 3x squared, divided by the derivative of the denominator, which I can see is going to be 4x to the third plus 2. And then I can say, okay, am I able to evaluate it now? After every use of L'Hopital, you should try to evaluate. And if it's no longer indeterminate, you're done. So when I try to plug in a 2 at this point, I can see, well, my numerator is going to be 3 times 2 to the second. That's 3 times 4. I'd get a 12. And instantly, I already know I'm done because no matter what, the numerator is no longer 0 or infinity. So you're done, no matter what the denominator is. The only indeterminate forms is 0 over 0 and infinity over infinity. If you don't get that, you're done. So I get the 12 in the numerator. I know I'm done. I go ahead and evaluate the denominator as well. That's going to be 4 times 2 to the third plus 2. We can say, well, 2 to the third is 8 times 4 is 32. Plus 2, we get a 34. So this is telling me that my limiting factor, and please do notice, when I plugged the 2 in for x, you must drop the limit notation. From this step to this step, the limit notation dropped. I had to still have it in here at this point because I hadn't plugged 2 in for x. The instant you plug a 2 in for x, the limit notation drops. We get our 12 over 34, which reduces down to 6 over 17. Now for the next one, I'm giving you the limit as x approaches 2 of 4 minus x squared over the sine of pi x. If I were to just think about this, I can say, well, okay, can I plug a 2 into the numerator? Nope, because it would be 4 minus 4, which is 0. Your denominator would be the sine of 2 pi, which is, again, 0. So I can say, well, that's just 0 over 0. That is indeterminate. L'Hopital should help. Every time you use L'Hopital, you must show me the h over the equal sign. This is still going to be the limit as x approaches 2. Derivative of the numerator is going to be negative 2x. Derivative of the denominator, derivative of sine is cosine. I keep the angle. Then I multiply by the derivative of the angle thanks to the chain rule. That's where that pi came from out front. So it was the cosine of pi x times pi. I went ahead and brought the pi out front. Now I'm thinking, can I evaluate at this point? And I know I should be able to, because in that numerator, I'm no longer going to have a 0. It's just going to be negative 2 times 2. I get a -4 up top. In my denominator, I'll get the cosine of pi x. That becomes the cosine of pi times 2. Well, cosine of 2 pi is the same thing as the cosine of 0. It's 1. I'd get 1 times pi down here. So pi times 1, I get a denominator of pi. Final answer of -4 over pi. Pretty cool problem. Now in the next one, this is one where I'll have some students that get complacent and they say, oh, okay, yeah, I can take derivative of the numerator and denominator and then evaluate. They'll do the same thing in this one and they'll say, well, hey, can't I call this the limit as x approaches 1 of 2x over 2? And then plug in the 1. If they did, they'd get an answer of 1, which is wrong. So if you use L'Hopital on a problem that is not indeterminate, L'Hopital leads to the wrong answer. So in this case, you do have to be very careful and say, okay, can I use L'Hopital? No. Why no? Because you can just plug a 1 in. You can say the limit as x approaches 1 of this, you'd get 1 squared plus 1. Your numerator's 2. Your denominator's 2 times 1 plus 1. It's a 3. You get an answer of 2/3. But I absolutely think it's cool that if you use L'Hopital when you shouldn't use L'Hopital, it'll lead you to a wrong answer. So just please be careful on that. For the next one here, we have the limit as x approaches 0 of e to the x minus 1 divided by cosine x minus 1. Now, I already know L'Hopital should be used on this one, but let's say hypothetically the one before did require L'Hopital, so I wouldn't know if this one needed it or not. There will only be one problem where you don't have to use L'Hopital. So I know it's needed on this one, but if I wanted to prove to myself, I'd say, well, I need to evaluate it at 0. E to the 0 is 1. Minus 0, still 1. Minus 1, that'd give you a 0 in your numerator. Your denominator would be the cosine of 0, which is 1 minus 1. This is another case of 0 divided by 0. That's indeterminate. So I use L'Hopital and say this limit is nothing more than the derivative of the numerator divided by the derivative of the denominator. Derivative of the numerator here, I'd get derivative of e to the x is e to the x. Derivative of minus x becomes minus 1. Now in that denominator, derivative of cosine is negative sine. And of course, derivative of a constant cancels out. So I'm thinking, okay, can I evaluate it at this point? Unfortunately, no. If you tried to plug in a 0, you'd get e to the 0, which is 1. 1 minus 1 is 0 in the numerator. Sine of 0 would be 0 in the denominator. This is still 0 over 0. That's okay. You use L'Hopital a second time. There's no limit to the number of times you can use L'Hopital. In this one, 2 is going to be enough, though, because when I take the derivative of the numerator again, I just get e to the x. Derivative of negative sine of x is negative cosine x. I now evaluate this at 0, which is why from this step to this step, you drop the limit notation, plug a 0 in for x, you get e to the 0 over the negative cosine of 0. E to the 0 is 1, cosine of 0 is 1, but we have a negative in front of it, so I get 1 over -1, which simplifies to be an answer of -1. Final answer. Now, for the optimization problems, you'll have a geometric optimization where I guarantee you, I'll tell you that you have a certain length of wire. In this case, it's 20 meters of wire that you're going to be cutting into 2 pieces. One of the pieces will be an equilateral triangle. The other piece is either going to be a circle, as it is in this problem, or I could switch up the problem and make the other object a square. So the other object will either be a circle or a square. In this case, we have the circle for the second object. And I said in every problem, the first object will be the equilateral triangle. Now, I'll be asking what amount of wire should be allotted to each figure to have the minimum total area. So the way I set up this problem here is I just said, well, okay, I know I'm trying to use 20 meters of wire. I need to allot a certain amount of it to an equilateral triangle, the other amount to a circle. I strongly recommend always using X for the perimeter of the equilateral triangle. That means you'll use the rest of the wire, which is going to be 20 minus x, for the circumference of your circle. Okay, now every single side of that equilateral triangle has to be the same length. So I know, well, that'll just have to divide x by 3 for all 3 sides. Now, I needed to analyze the triangle a bit better because the area of a triangle is 1/2 base times height. And the height is certainly not x over 3. I had to find that. So I said, well, okay, in this equilateral triangle, if I look at a bigger picture of it, we know that this side would be x over 3. The entire base would be x over 3, but half of the base would be x over 6. So I could draw a perpendicular bisector with the base of this equilateral triangle, and that's going to form the height of the triangle. Now, I need to find out what the height of that triangle is so I can plug it into my area formula. No problem at all, because now we know that that height is merely a side of a right triangle within that equilateral triangle, where the hypotenuse would be x over 3. So I went down here and I said, well, anytime you have a side of a right triangle, that side's length is always going to be the square root of the square of the hypotenuse minus the square of the other leg of the triangle. So I can say, well, in this case, it's the square root of x over 3 squared minus x over 6 squared. Then I needed to simplify that out. I already knew that this would be x squared over 9. This would be x squared over 36. To make sure that that simplified nicely, I went ahead and got a common denominator and said, well, x squared over 9 is the same thing as 4x squared over 36. I'm subtracting 1x squared over 36. So that would give me on the inside the square root of 3x squared over 36. Well, that 3 in the numerator doesn't simplify inside the square root, so you'll see I put it as the square root of 3. Excuse me. The square root of x squared came out as an x, and then the square root of 36 in the denominator simplified to be 6. Okay, so now I plugged this into my area of a triangle formula up here, so I could get the area of the triangle in terms of x. So I can say, well, 1/2 base times height becomes 1/2 the base x over 3, the height square root of 3 over 6x goes right there. Multiply across, you're going to have x times x is x squared. You'll have in the denominator 2 times 3 is 6 times 6 is 36. And you have a square root of 3 in the coefficient, in the numerator of the coefficient, multiplying the x squared. So I get the square root of 3 over 36 x squared. That is the formula for the area of the triangle. But now we're trying to find a formula for the total area of both objects so that we can minimize that total area formula. Okay, so down here is where I thought about the circle. I said, well, I know in a circle, and I know in this particular circle, I'm going to allot 20 minus x for the distance around the circle, otherwise known as the circumference. And so I can say, well, if I do that, the circumference is equal to 2 pi r. And yes, you need to keep that in mind for the test if you don't already have your circumference formula memorized. Circumference of a circle is 2 pi r. And I know that that's going to equal the amount that I have allotted for the circumference of the circle, 20 minus x. So I need to solve for r in this, and that's just going to be 20 minus x divided by 2 pi. Now, I know that the area of a circle formula is pi times r squared. Well, I just figured out what r needed to be. If the circumference is 20 minus x, this has to be the value for r. So all I need to do is plug this into my area formula, and you'll see I did that up here. Area formula with respect to x is just going to be pi times my radius formula, 20 minus x over 2 pi quantity squared. Okay, so now what I did at this point is I said, well, I know that if I squared the denominator, I would get 4 pi squared. One of those pi's is going to cancel with the pi I'm multiplying by. That's why you see a 4 pi in the denominator. My numerator is just 20 minus x times 20 minus x. That's where you're getting 400 minus 40x plus x squared. Please be careful and don't tell me that that numerator is just 400 and then plus x squared. A binomial squared is always a trinomial. If you need to write 20 minus x times 20 minus x to get to this trinomial, please do that. Now, what I did just to make this area formula a little more useful is I wrote it in descending order, and I went ahead and distributed the 4 pi into each coefficient I had in the numerator. So I had 1 over 4 pi times x squared minus 40x over 4 pi. I said, well, minus 40 over 4, that's going to reduce down to minus 10 over pi times x. And then my last one, 400 over 4 pi, 400 over 4 reduces down to 100. I'll get plus 100 over pi for the constant. Now, this would be the area formula with respect to x of my circle. I needed to minimize the total area, so I had to come up with a total area formula. And I said, well, total area is just area of the circle plus area of the triangle that I did up here. So I saw that, well, the area of the triangle only had an x squared term. This one had an x squared term. I went ahead and I added the coefficients of x squared. That's where this square root of 3 over 36 plus 1 over 4 pi x squared came from in my total area equation. So that's the sum of the coefficients of x squared, and I preferred to keep it exact. I didn't want to bring in any messy decimal approximations. Bring down the rest of your area formula. You'll have minus your 10 over pi x plus 100 over pi. And of course, the area of the triangle formula didn't contribute anything to these last two. It just contributed this portion right here. But this is my total area formula. Now, in order to minimize it, we just say, well, we need to find the critical points. Critical points are when the derivative is equal to 0. When I took the derivative here, this 2 came down, multiplied the coefficient. When it did, I just said, well, okay, when it comes down, that first term could be 2 on the root of 3 over 36. But instead of writing that, I just said, well, that's going to reduce down to an 18 in the denominator. Similarly, the 2 could have come down into this second term and made 2 over 4 pi. It's better just to call that 1 over 2 pi. So this is what happened when that 2 multiplied into both of the coefficients of the x term. Then I dropped the power to 1. Derivative of minus 10 over pi x is just minus 10 over pi. The x cancels out, becomes x to the 0 power. We set this equal to 0. When I do that, the 10 over pi would move to the right-hand side. And then in order to solve for x, you'd have to divide by its coefficient. That's why I said x is going to equal 10 divided by pi times the group square root of 3 over 18 plus 1 over 2 pi. And you'll see there, I get the answer 12.464. A lot of people would make calculator errors on this. So let me make sure you're comfortable with that. If I tried to put this into the calculator, I'll say, another thing that will be beneficial on this test is to make sure your calculator gives you decimal answers. So you don't want your answers to be on automatic. You want them to be on decimal answers. That's under the mode menu, and it should be the second page. But now, once I do that, I can say, well, okay, this problem, and I'll do fraction. Sorry, guys. Alpha y equals fraction. I have 10, and then we want to take that 10 and divide it by the denominator there. My denominator has the factor of pi times the group, the square root of 3, I can get out of the square root, divided by 18, plus 1 divided by, and here's where some people would make a mistake. I could have went ahead and did another fraction in the denominator. I could have used alpha y equals and put another fraction here. I chose not to, but it would be wrong if I did this, and I need you to understand why. That is not 1 divided by 2 pi. This is 1 divided by 2, and then multiply that answer by pi. I need to make sure to divide all of 2 pi into 1. So in order to get this correct, I'd have to do parentheses 2 pi there. I'm dividing 1 by the entirety of 2 pi. I can close out my denominator now. This should be gorgeous. And it is. So we get our answer for x is 12.464. You can say, well, x is the amount of the wire that should be allotted for the equilateral triangle. So you'll see, I ask you in the question how much wire should be allotted for each figure. So I do want you to answer that. And you can say, well, the answer I got for x, that's how much should be used for the triangle. And then we know the answer for y is just going to be 20 minus that. So I could have just said 20 minus second answer, and you get your 7.536 rounded. I normally like answers rounded to 3 decimal places unless I say otherwise. And on this test, for the last 2 problems, I did say otherwise to 4 decimal places. But this one, 3 is more than enough. So that's probably the trickiest problem on the test. Please make sure you go back and understand the different components. You'll have to get the area formula for the triangle, area formula for either a circle or a square. So if I had done triangle and square here, you'd have just said, well, 20 minus x is the perimeter of the square. So every side would be 20 minus x over 4. And then you would say, area of the square would be 20 minus x over 4 quantity squared. You'd have the same thing up here, and your denominator, instead of being 4 pi, just be 16. So it'd be extremely similar. Up next, we have another optimization problem. This one's more of the, well, the next 2 both are more of the business applications. It says a manufacturer estimates that when X units of a particular commodity are produced each month, the total cost will be X squared plus 3X plus 300, and all units can be sold at a price of $5.97 minus 2X. Determine the price that corresponds to maximum profit. This problem's just like the ones I did in the notes lecture. So if we look at that, you can say, well, okay, what are we supposed to remember from that? Well, supposed to remember that profit is nothing more than revenue minus cost. Revenue in an example like this, the total amount of money you bring in, it's the number of items you sell times the price at which you can sell them for. And then the cost function already takes into concern the cost of X items. So do not multiply the cost function by X. It already takes that into consideration. Now, for my revenue function, which was X times P of X, it becomes X times the price function P of X that was just given in the problem, 597 minus 2X. So then once I do that, I can say minus the cost function that I was given in the problem. And please do remember, you're subtracting off the entire cost function. You have to say minus the parentheses of the cost function. Remember, every term is subtracted. Now, when I wanted to pull all this together and get it into a nice quadratic function, I can see my first term is going to have a negative 2x squared. I would subtract x squared for negative 3x squared. I would have a 597 minus 3 for the coefficient of x, 597x minus 3x. That's where the 594x came from. And then I don't have a constant in the first term, but we know that we're going to be subtracting 300 from that. So this would be my overall profit function. And then I can say, well, I need to find where that profit function is maximized. And I know the critical point is going to be the one that maximizes it because it's a negative quadratic. Any critical point of a negative quadratic will maximize it. So all I have to do is take the derivative, set the derivative equal to 0. My derivative here, negative 6x to the first plus 594 is equal to 0. So then I can say, well, then 6x is going to equal 594. Divide by 6, you get x equals 99. Please don't stop prematurely on these problems. I could see a student getting happy and circling 99 and moving on. That would be terrible because 99 is not the final answer. That's just where the maximum profit exists. It's going to exist when 99 units are sold. But now if you look at the problem, I'm asking you to determine the price that corresponds to maximum profit. So we already know the maximum profit occurs when 99 units are sold. Well, you need to put that 99 units into your price function. What price is going to have to be set in order to sell 99 units? So the price of 99 would just equal 597 minus 2 times 99. And we can see that that's 597 minus 198. You get $399. We know that the price that maximizes profit is going to be $399 in this case. Now, for the next one, I will give you a problem in number 10 that's going to refer to the cost function in number 9. And I'm wanting you to find the minimum average cost. Now, whenever you're thinking about the minimum average cost, why wouldn't you minimize just the normal cost function? Because you can say, well, the minimum of the cost function would just be when you don't make anything. That's when the costs are at a minimum. You just don't make anything. But you don't want to minimize that because then you never produce anything. So rather than find the minimum of the cost function, you would say, well, what if I find the averaged cost function? We want to find the average price per item made, and we would like to minimize that. Okay, well, if the cost function is the cost of X items, the average cost of X items is always your cost function divided by the number of items you make, which is X. So you can just say, well, that's very easy to find then. Your average cost function is just your cost function divided by X. This X distributes into every term in the numerator. You'll get X plus 3, and then plus 300 over X. I would rather write as 300X to the negative 1. Now, for that average cost function, I'd like to minimize it. Well, the minimum is going to occur when the derivative is 0. So I take the derivative, and it's really easy to take the derivative. Derivative of X is 1. Derivative of any constant 0, so the second term drops out. Derivative of 300x to the negative 1 would be minus 300x to the negative 2. I preferred to write that as minus 300 over x squared. We set that equal to 0 to find the critical points. When I do, I just move the 300 over to the right-hand side, 300 over x squared over to the right-hand side. Then you can say, well, all I have to do is multiply by x squared on both sides, and you'll get x squared is 300. That means we know x is equal to the square root of 300, which is approximately equal to 17.321. Now, it does not make sense within the context of this problem to say, hey, the minimum average cost occurs when 17.321 items are made, because you can't produce and sell 17.321 items. You need to produce a whole number of items. So you can just say, well, just round to the nearest number. The minimum average cost is going to occur when 17 items are made. Now, again, I'll get students that think, ooh, the minimum average cost is $17.32. Absolutely not. X is the number of items that need to be made in order for the minimum average cost to be achieved. So that's why X only makes sense as a whole number value here. Well, we can make 17 items, and that's when the minimum average cost is achieved. Well, what is the minimum average cost? You would plug 17 back into your average cost function. You could either plug it into this or this. It's going to be the same answer. I chose the first one and said, well, that's just going to be the cost of the average cost function evaluated at 17. That's why I have 17 bar over it. I'm plugging it into the average cost function. You get 17 squared plus 3 times 17 plus 300 all over 17 in the place of the X. And when I did that, I got an average of $37.65. Of course, we do round that to 2 decimal places since you're talking about how much money it is per item. Now, if you think about this, minimum average cost was $37.65, yet they're going to sell it for $399. That's a pretty good marketing plan, they're going to be making quite a bit of profit if indeed they could make the items for this and sell them for this. That's pretty sweet. Now, for the last two problems, they're both Newton's method problems. I'll give you a problem where I ask you something like, find the root of some specific number with Newton's method. Now, that doesn't mean, hey, I can just go to my calculator. He's wanting me to find out what the fifth root of 340 is. I know fifth root's the same thing as the 1/5 power. So yes, I know this is the answer here. That's going to be my final answer. You can't just do that. There would be no calculus to that. So please keep in mind, you could put a correct answer to 11 and 12 and not get a single bit of credit. I need to see evidence that you're doing Newton's method. So everything that I have on my sheet, you would need to have on your sheet for the test problems here. So for number 11, you're trying to evaluate the fifth root of 340. The steps to do that. You first have to say, well, okay, let's let x equal what you're trying to evaluate. Now you have to get a function f of x that is differentiable, that doesn't just have a constant answer. So you can't simply just say, well, can I let f of x equal x minus the fifth root of 340? No, because the derivative of that would just be 1. It has to have a variable derivative. So that's easily fixed. You can say, well, all I have to do is get rid of the fifth root by raising both sides of the equation to the fifth power. That gives me x to the fifth is 340. Now, for Newton's method, f of x always has to be a function set equal to 0. So you'll see that's why I said f of x is going to equal x to the fifth minus 340. And then the derivative of f of x is just the derivative of x to the fifth, which is your 5x to the fourth. Now, Newton's method says you can find the roots of f of x when it's going to be equal to 0 by setting an initial guess and then saying every successive guess is the preceding guess minus the original function evaluated at the preceding guess divided by the derivative evaluated at the preceding guess. I will always give you your original guess here. So on this test, it said original guess, use an initial guess of 3. Okay, so using that initial guess of 3, we would have to plug it in and say, well, all right, my first refined guess is going to be 3 minus the function evaluated at 3 divided by the derivative evaluated at 3. You can make that so much easier if you'll use your calculator on these. And again, for the Newton's method problems specifically, guys, you'll want to make sure your calculator is giving you decimal answers. So that's where you need that answers to be on decimal. You don't want it to perhaps give you fractions for this. You want to see the nice decimals in there. Now, to get this in there, you need to make sure 3 is in as an answer. So I just hit 3, enter. So right now my calculator is, if I were to hit answer, it's going to assume I'm referring to 3. I'm going to do that. I'm going to say, all right, let's take that 3 and I'm going to store. You'll notice it's saying, oh, I'm going to take that answer and store it in for x. Then hit colon. Colon is alpha decimal. So alpha decimal, and the colon pops up. Okay, now once I do that, I type in Newton's method. Newton's method in this problem and in every problem is just going to be your x minus f of x. Well, what's f of x? F of x is your function right here, divided by f prime of x. To make this look nicer, since I know it's going to be a fraction, I'll do alpha y equals fraction. My numerator, f of x, that's going to be the x raised to the fifth minus 340. My denominator here, 5x to the fourth. So I have x minus f of x divided by f prime of x. Right now, it's going to plug a 3 into that. Well, that's what I want it to do. My first refined guess, I get the 3.239506173, and I will want to see every bit of that number written out. And then you say, well, okay, are we done? No, because we need to make sure we're accurate to 4 decimal places before quitting. Right now, I don't have any knowledge of decimal place accuracy by the first refined guess. The only way you're guaranteed that your answer is accurate is that Newton's method is going to repeat to that number of decimal places, and that's when you know you're accurate at least to that far. Okay, so in order to get to the second refined guess, all I have to do is hit enter again. And the reason this works so nicely on your calculator is because now your calculator is thinking of this as the answer. So it's going to take that answer and plug it into your equation. And you can say, well, my second refined guess is the 3.20904,338. We get that answer. At this point, by x2, I would know I have, well, 1 decimal place accuracy. I know it's 3.2 at that point. I need at least 4 decimal places accuracy. So I just hit enter again. It takes that answer, plugs it into the expression. And now you'll see we get 3.208453967. At that point, I would have 2 decimal place accuracy. I'm not certain whether the next number is a 9 or just an 8. So I could say, well, all right, let's do a 4th refined guess. By the time you get to the 4th refined guess, you can see that a whole bunch of numbers repeat, 3.20845. The next number after that could be a 7 or 9, or could be between them at an 8. But I know that no matter what that is, it would round that number up. So to 1, 2, 3, 4, to 6 decimal places, it'd be 3.20845. I would be confident with that. But I only ask 4 decimal places. So I can say, well, okay, to 4 decimal places, since the problem asks that, I can say it's 3.2085. Now, just out of curiosity, you may say, well, is x sub 4 correct to all the places on the calculator, 8 decimal places? And yes, it is, because x sub 5 would repeat. So we're already sure x sub 4 is correct all the way out to the very end of that, but I did ask for 4 decimal place rounding, so final answer would be this in this problem. Now for the next one, I give you a function, in this case, f of x is equal to 3x cubed, sorry, not f of x, your function is 3x cubed is equal to 2x minus 5. F of x always has to be the function set equal to 0. So that's why I went ahead and pulled these terms over with the 3x cubed and said, let's let f of x equal 3x cubed minus 2x plus 5. And then the derivative of that expression would be 9x minus 2. Now, at that point, I can go in and say, well, all right, I need to find the roots of this function. And I do that by using Newton's method. This time I told you to use an initial guess of -1. So going back to my calculator and trying to show that on this problem, I can say, okay, I need to make sure -1 is in as an answer. So I hit -1, enter. Now it's time for Newton's method. You store that -1 in for x, hit colon, alpha, decimal, then type in Newton's method for this problem. Well, Newton's method for this problem is going to be x minus, and again, it's probably easier if you use the fraction button, x minus, well, right here's my f of x and f prime of x. It's always x minus the function divided by the derivative evaluated at these values. So I'll type in my function here, 3x raised to the 3rd. And then we have minus 2x plus 5. My denominator here, 9x raised to the 2nd and minus 2. Okay, so I get those entered in and I'll try to make sure it matches these. I'll say, all right, the original guess I give you, we always label that x sub 0 is equal to that. When I plug -1 into this function, It's going to give me the first refined guess is negative 1.571428,571. So that'd be like negative 1 4/7, by the way. So that's like negative 11/7. But the decimal is better in this case anyway. At this point, I don't have any decimal place accuracy. We know the answer is somewhere between negative 1 and negative 1.57 at this point. So then you would plug this first refined guess into your function, and Newton's method would tell you it's equal to negative 1.3984 for 3131. So at this point, I still don't have even one decimal place accuracy, and I'm on my second refined guess. I plug this back into my function. Calculator makes it easy. I just hit enter again. And now at least I have one decimal place accuracy. I could say if I had to round this to one decimal place, it's going to be negative 1.4. I'm certain of that. But unfortunately, I don't know anything beyond that. So I don't even have two decimal place accuracy still yet. But in my fourth refined guess, I do see that the negative 1.37 part did repeat. So I know I'm accurate to two decimal places, but the third decimal place could still either be a 2 or a 1. Well, and I guess either way it would round to be a 2, it looks like. But I would not have 4 decimal place accuracy. So I could say, well, you've got to do it again. By the time you get to your fifth refined guess, we can see that we have a bunch of terms that repeated. It looks like the first 1, 2, 3, 4, 5, 6 terms all repeated. Now, we wouldn't notice 6 decimal places since this would round up and this would round down. Doesn't matter because I'm only asking for 4 decimal place approximation. So we can say in our problem, our solution for the root would be negative 1.3717. And that's the answer that you'll see over here. Just out of interest, if you tried to plug x sub 5 in, are we already at the actual answer as far as the calculator can go? And we are. So correct to 8 decimal places, really, if you wanted to put all of that. But since I asked for 4 decimal place answer, that's all we need. All right, guys, this will be your fourth test of the semester, or your preparation for your fourth test of the semester. If you have any questions, let me know.